Hello everyone, today let's take a look at quantipose number 52, definitely a pretty interesting one, and basically what we want to do in part A is find the value of this sum right here for any positive integer, and we're going to use what we find in part A to kind of give a brief proof of the inclusion-exclusion principle, which we're going to use a lot later and we have been using. So let's start off by looking at part A. So what we did in previous parts was we used the binomial theorem to show that the sum of these binomial coefficients is going to be equal to 2 to the power of n. So now for part A of this question, the only difference is that we have this negative 1 to the power of k out front. So now let's think about what this is going to equal. Well, first let's just start with an example. Let's say n is 5, then what does this equal? We know that when we plug k equals 0, that's going to be our first one. It's going to make the first one positive. We're going to have 5 choose 0 to start. And then when k increments to 1, this is going to become negative, and we're going to have minus 5 choose 1, obviously. So this sum right here is just going to end up being equal to the alternating sum of the binomial coefficients. And what's the answer in this case? Well, you can see when you work all the terms out that everything's going to cancel and you're going to be left with 0 here. Now, just to be thorough, let's just do one more example where n equals 6. So this right here is our alternating sum for 6 elements, and when we work it out, we again get 0. Now we can think about why this is the same way as before, first using the binomial expansion. So we've already derived this formula. This is the binomial theorem. Previously, when we were showing that the sum without the negative 1 to the k was equal to 2n, we let x and y both be equal to 1. So now we ask ourselves, what numbers can we plug in for x and y such that the right side of our equation will look like this? So you can kind of see that if we plug in negative 1 for x and 1 for y, so we have negative 1 plus 1 to the power of n, well then that's going to be equal to this right here, and this is exactly what we have up here, right? And you can clearly see negative 1 plus 1 is 0, 0 to the n is also 0, so then this is always equal to 0 for any n. So that's how we prove it using the binomial theorem, but we can think about it more intuitively if we do it like this. So the first thing to see is that in all of the examples of our expansion, right, we're going to be adding up all of the even subsets, right, when we choose 0 elements, 2 elements, 4 elements, or 6 elements, and we're going to be subtracting off all of the odd subsets, right, where we choose 1 element, 3 elements, or 5 elements. And since we just showed that when we combine them, we get 0, that must mean that the number of even subsets must be equal to the number of odd subsets, but how can we think about it intuitively? So I drew kind of a little diagram, and let's look at the example when we have 6 elements, right? So imagine in my universe, I have 6 different elements, and now I've chosen some of them to be in this subset S here. So S either has an even number of elements or an odd number of elements, right? Because a number can obviously only be even or odd. Now imagine that there's some element X that is not in this subset S. But then if I add x to the subset, right, the parity of s is going to flip, right? If it was even, then now it's going to be odd because we added an element to it. But if the number of elements was odd, then when we add x, it's going to be even. So when I add x into s, the parity of s will flip. And also if x is already in s, then when I remove it, the parity will also flip, obviously. Also, we showed that in the previous roadmap problem, when we are making subsets, we can either choose to include or exclude any element, right? So there are 2 options here. We could include or exclude element number 1, include or exclude element number 2, etc. So let's look at our example. When we have 6 elements, one of them is x. We can see that we have 2 options, either include or exclude. Same for every single other element. So we have 2 to the 6 different subsets. And for x, you can choose to include or exclude it, right? So if we choose to include it, then we have 2 to the 5th subsets that include x. And if we choose to exclude it, then we also have 2 to the 5th subsets that include x, right? So all this serves to tell us is that the number of sets that include x is going to be equal to the number of sets that exclude x. Now what we can do is just kind of enumerate these sets. Let's just take every single set that doesn't include x, right? And then let's just add x to it, right? Let's say now I have x in this set, and now I have x in this set, and we can pair them off kind of 1 to 1 like this. And notice that when we add x, we are flipping the parity. So if this set had an even number of elements, now it has an odd number of elements. And if this one had an odd number, now it has an even number. So what exactly have we shown here? Well, the number of sets including x is equal to the number of sets excluding x. We can pair all of these off 1 to 1, and they're going to have opposite parities. So what does that imply? Well, it just implies that the number of even subsets is equal to the number of odd subsets. And that's all just to show that when we add up all the even subsets, as we do here in the alternating sum, and we subtract off the odd ones, well, we're going to have equal in each group, so they should equal 0, and that's exactly what we found. So sorry about that, I went on a little bit of a tangent there, but I think it's important to understand, even if that last part was a little convoluted, the important part is that we can use the binomial theorem to derive that the alternating sum of the binomial coefficients is equal to 0, and we're going to use that in the inclusion-exclusion proof. So now let's actually go back and look at part B here. So part B is asking us to use that result in part A, which is a big hint, to give a short proof of inclusion-exclusion, right? And remember, the inclusion-exclusion principle is that the union of a bunch of sets, if they have overlap, is just equal to summing up the individual contribution from each set, but then you're going to overcount some. So you have to subtract off the intersections of some sets and then add back on the triple intersections and etc. So the hint kind of tells us how to get started. Let's consider an element x that belongs to exactly k of the sets a sub I, and then we just need to determine the number of times x is counted on the right-hand side. So let's just set up the problem. Imagine I have a bunch of subsets. I know it's not perfect drawing, but imagine I just have a Venn diagram here. Each circle represents a different subset, and imagine x exists in k of these subsets. So imagine, like, for instance, x exists here where there's some overlap between some of our subsets. So this is the left-hand side of our equation. What's it trying to do? Well, it's just trying to calculate the union of all these sets, which means, let's say, for instance, we have these elements here, maybe these elements over here, a bunch of elements. We just want to calculate the total number of elements that exist within the union of all these circles, right? So for instance, in this case, what we want is, well, we have 1, 2, 3, 4, 5, 6, 7. We want this to be equal to 7. So obviously with inclusion-exclusion, the problem we're trying to solve is that when we calculate the magnitude of just this circle, let's say, and then we calculate the magnitude of this circle as well, you can see that x is going to be counted multiple times, same with f. So let's go back to what we were saying originally. We say that x belongs to k subsets. So what are we trying to see in our final answer? Well, we basically want this x to only be counted one time in our final answer. So no matter how many subsets it's in, if it's in here, if it's in 10 subsets, we want it counted one time. Also, let's say if x was not within the union of these sets, we do not want it counted at all, right? We want it counted 0 times. So this is what our desired outcome is. So let's show that this right-hand side of the equation does exactly that. So again, let's reset up the problem. Let's say x exists in k subsets, exactly k subsets. So first, let's just look at the first part of the right-hand side of our equation, where we're just summing up the magnitude of each set a sub I. And as we work through the equation, let's just keep a tally of the number of times that x is being counted. So since x belongs to k subsets, when we count the magnitude of each individual set, x is going to be counted k different times. Now the second part of our equation, where we subtract off the intersections, how many times is x going to be counted here? So in order for x to be counted in this term, both of these subsets here need to both contain x. So for every single combination of subsets that contain x, x is going to be counted one time in this term. So how many combinations of two subsets are there that contain x? Well, x exists in k subsets, so there's going to be k choose two different combos. Now on the right-hand side of our formula, let's move on to the next term where we add back all the triple intersections. So in order for x to be counted here, x obviously needs to exist in all three of these subsets, and x exists in k subsets, so there's going to be k choose three different combinations of three subsets that could contain x. And you can clearly see the pattern emerging here. When we go on to subtract the number of intersections with 4 elements, we're going to get k choose 4. That's the number of times that x will be counted there, and etc. Well, does this look familiar at all? Well, it should, because it's exactly what we were doing in part A, pretty much. This term k is also just known as k choose 1, right? So now I've made more space, but what is this sum right here going to be equal to in formula form? So let's do it out. Obviously, we're taking a summation here. We're going to have some k choose j, where j is the iterator. So j is going to be incrementing this bottom count here in the combinations formula. So j is going to start at 1, as we saw, and it's going to go all the way up to k. And the series is alternating, so we need -1 raised to some power of the iterator. But obviously our first term is not negative, it's positive. We want this first term to be positive, right, when j equals 1. So let's just subtract 1 here. And that'll make our first term positive. And then when we plug in 2 for our second term, we're going to get 2 minus 1 up here, which is going to be 1. So this is going to be negative, and it'll work correctly. And for part A, this is the formula that we derived. You can see it's slightly different. Our iterator starts at 0 here, and it has a different power up here. So this equation right here is counting the number of times that x got counted when x existed in k subsets. So we would expect that this would equal 1 when k is greater than or equal to 1, right? When x exists in more than one subset in our union. And we would expect this to equal 0 when k is 0, right? When x exists in 0 subsets. All right, so coming back down here, let's get our iterator to be the same as it is up here. So let's just say that this is equal to, well, let's pull out our first term, which is going to be n choose 0, right, positive, and we're going to add on now the sum from I equals 1 to n, negative 1 to the I, n choose I. This is exactly the same as this. Now, what is n choose 0 equal to? Well, we know it's equal to 1, so then this right here is going to be equal to negative 1, right, if we subtract off 1 from each side here. Right, so now we're just going to be left with this equation over here. And now this is almost the same as this, but we also have this negative 1 up here, right? We have negative 1 to the power of negative 1 times negative 1 to the j up here, right? If you expand this out. So to make this bottom part the same as the top, let's just multiply each side of this by negative 1 to the power of negative 1. And when we do that, you can see that, well, we know negative 1 to the power of negative 1 is just 1 over negative 1, which is also negative 1. So now we get this right here, right? Negative 1 times negative 1 is going to give us 1, and this is exactly the equation up here. So what does that mean? Well, this is equal to the number of times that x is counted, right? And this is equal to 1 when k is obviously greater than or equal to 1, right? Because if k is 0, this doesn't even make any sense. Our iterator is starting at 1, and it's going to 0, so this isn't even going to run, and we're just going to get 0. So that kind of concludes the proof of the inclusion-exclusion principle. We showed that if x exists in k subsets, then the number of times that it's counted in this part of the equation is going to be 1, which is exactly what we want. Going back to our Venn diagrams, we just wanted to count everything once when we're calculating our unions.